somebody else shows up, and you were asking about Lillian?
Yeah, no, Lillian's there.
Okay, I see, I just saw Lillian.
Hey, Lillian.
We are very fortunate to have Larry Lawver here again today to talk to us. I'm not going to go through all the bio information. If you didn't catch it last night, too bad. I will say that one thing I didn't share yesterday evening is that Larry's actually a neighbor of ours. He lives on the correct side of the town of DuBois,
West side.
which is the west side. Nothing against people to the east, except that's the wrong side of town, apparently, Lillian.
Oh, that's the opposite.
So Larry's here and going to follow on from last night and talk in particular about the circumpolar current, and as you see, the Georgia microcontinent.
Thank you. I know Lillian wasn't here last night, but was everybody else here last night, or? No? Okay, all right. I was going to leave out a whole bunch of stuff because it would kind of be a repeat, but I'll go through it somewhat quickly. South Georgia is an island. It was a British protectorate, and now it's, I think, it was underneath the Falkland Islands, and now it's semi-independent, or something like that. But anyway, it's a fabulous place, and as a lot of people know, it's where Shackleton wound up, and then he hiked up, actually just to the west of here. This is a wonderful picture, and we were setting up a GPS station on Anakov Island, and so it's looking over this way, right to the center of the island. It's like 10,000 feet high, and it's just, we'll get to this slide eventually, but we had a cruise on the Nathaniel B. Palmer, which is a NSF ship that's run by the National Science Foundation, and we also had a middle school teacher from Flagstaff, Arizona there, and she was representing the Polar Track, which is used to be the DEA Experiencing Antarctica, and then it was the DEAA Teachers Experiencing Antarctica and the Arctic, and now it's eventually Polar Trek. But they try to send out teachers, and they'll come out on the cruise, and then they'll report back to their kids. And if you're really lucky, which I was incredibly fortunate, the first Polar Trek teacher we had was a guy named Steve Stepanovsky, and I actually took him to Antarctica, and then we went to the Arctic, and then he had a third cruise with us, and he put up all these modules and stuff like that, and now he's working for some science education thing back in DC or something. So, and he told the story that I hadn't heard till quite a bit later, that he was at some meeting at I think it was NSF, and there were all these talking heads around, and finally he raised his hand and he said, "Since I'm the only one that's been in a classroom this week, this is what it's really like." So it's really, some of these things are really wonderful. And then I'm from the Jackson School of Geosciences at the University of Texas at Austin. And as I say, I unfortunately still have a job, but I hopefully will be living in DuBois next year for at least 6 months, and hopefully more after that.
If you did this in 1408, you aged remarkably well.
Well, no, it's 14 is for 2014, and it's 8th cruise of 2014. So, but I have aged because I in fact, the Palmer, which I still consider a new ship, I think I was on the second cruise they had. It was certainly the first geophysical cruise, and that was in 1993 or something like that. So now it's getting to be somewhat old ship. But anyway, all the students now do all this stuff, and so I figured I had to do an outline. Quick introduction, short explanation of plate tectonics. People last night heard much longer plate tectonics history. Satellite-derived images, and then Mesozoic to recent ocean circulation, according to me, and then how the Antarctic Circumpolar Current may have developed. And the reason why I'm talking about the Antarctic Circumpolar Current is I think everybody knows that Antarctica has all sorts of ice sheets over it, and most people have dated those ice sheets back to about the Eocene or Oligocene boundary, which is about 33.5 million years ago. And for a long time, people made the presumption that the Antarctic Circumpolar Current developed because Drake Passage opened. And Drake Passage is the moving of South America away from Antarctica and essentially opening up a seaway through there, which I'll get to. On this cruise, it was absolutely awesome. We got to go to some places on South Georgia that nobody ever gets to go to. And I'll probably forget, but Anakov Island, which is where we were installing that last station, is a special protected area. And it's even more special than that. And they refused to let anybody on the island. And I think the only way we got permission was when we first went to Bird Island, where we installed the first station. We actually brought them fresh eggs and everything else, and they hadn't seen a ship in 6 months, and so I think they gave us a good mark for that.
May I ask, the GPS station, did you just use a simple device, or did you have to build
No,
some sort of structure?
you'll see that.
Oh,
it has solar panels and
Oh.
truck batteries and all sorts of other stuff. These are major installations that hopefully will stay there for quite a long time. Originally, when we applied for this grant, we tried to be really frugal, and we only asked for 2 years, and they said, well, you have to take anything out within the period of the grant, so they said rewrite it for 4 years, of course, no more extra money. And so I then immediately turned to my co-PI, Ian DL, which somebody last night had been out to sea with Ian in 1970. And I turned to Ian and I said, do you realize how old you're going to be when this expires? He's 80 this year, so, and still working full time. So, plate tectonics, at least I did, and I think a few other people did when we were in junior high, but I think Sue said you were in the 4th grade or something.
Yeah.
And you sit there and you match up South America and Africa, and they're like puzzle pieces, and it's obvious that something happened to rip them apart. And this dates back to Teddy Bullard and Everett and Smith in 1965. And the red areas are overlaps, and the blue areas are gaps, and they overlap there in the Niger deltas where all the sediments come out. So it's really hard to get exactly where the ocean ends and the continent begins.
You know, you said something last night that I was completely unaware of, but I believe you said that Wegener, back in the 20s or 30s, actually identified the San Andreas for what it was. And that surprised me. I guess I hadn't realized he was...
I had not realized that either until I was, because, there's this whole thing that Alfred Wegener was the one that started continental drift of plate tectonics and stuff like that. And then I found out that actually Frank Taylor had done it in 1910. But then I found that Wegener thing from 1929, and he actually had the San Andreas Fault.
That's surprising.
Yeah, I was stunned when I saw that, but he had the right lateral offset on it and everything. This is just a general overview of plate tectonics. Somebody last night kept asking me, well, how many plates there are? Well, it all depends upon how you define a plate.
And he's not here.
And then Julian wants to come up with a new lexicon of plates.
Well, luckily Julian's not here, so I don't have to mind my words. I first met her in, I think, 2003 in Florence, Italy, and that was just before she started her website about anti-mantle plumes. I firmly believe in mantle plumes, and I actually firmly believe that they're actually what break the continents apart. And South America and Africa split apart in about 132 million years because the Paranal mantle plume came up and actually hit underneath the South American craton, but the continent actually broke actually between cratons of much different ages. And it's really interesting because sometimes the older one would be on South America and sometimes the older one would be in Africa. And it was like tearing a piece of newspaper along the grain as opposed to trying to tear it across the grain. And it got up to this area here, and it actually got offset into a little Potobo and then got the basins up there, and it sort of spun its wheels and it opened the southern part of the South Atlantic, and then finally in about 118 million years ripped that apart. And Sorry if I'm losing the people that weren't here last night, but.
So does, by that comment you just made, does that mean your current thought is that essentially the spreading centers are pushing, or at least initiating?
I think that the largely
And
is
the
probably.
broader question is,
Yeah.
what's causing the plates to move? Are they being pulled or pushed?
Well, I think it's a combination of both, but I think the major factor, and if I had a lot longer to show you the magnetic anomalies of the Pacific Ocean, you can see, particularly in the Southwest Pacific, which John knows about, where all these back arc basins open, and as the Fiji Basin and the Lao Basin and stuff like that, the trench sort of swung around in an arc, and you can see that reflected in the magnetic anomalies that were coming off East Pacific Rise. So in my mind, it's clear that it was being pulled, and as the pulling direction changed, it actually changed the spreading direction way over at the spreading center. On the other hand, I think to rift the continents apart, you have a mantle plume that doesn't always rip right where the mantle plume comes up. It rips nearest. It's just like smoke coming up in your ceiling. The smoke, the fire may be over here, but the smoke winds up at the peak, and so it comes around and stuff. And this was just showing relative motion in North America and Pacific. And what I mentioned last night is I was incredibly fortunate in my background, because when I started out taking geology, they were still talking about vertical tectonics and myogeosynclines and useosynclines. And finally, I asked the TA, I said, this just doesn't make any sense. And he said, well, if you promise not to tell anybody, this is what's actually going on. And they just had a major symposium that talked about all sorts of different factors, and it became very clear that there was 400 kilometers of 5 to 6 million year offset on the San Andreas Fault. You can't do that with vertical tectonics. And so that was one of the major things that started out. And this was the slide that I showed last night. Actually, standing here, I could read these things much better. But this is paleogeography, and this is it's less than 500 feet and greater than 500 feet thickness. And you can match these things up, and these were deep water deposits there and there that went across right into shallow stuff. And so, there's all sorts of reasons why those things had to be offset that far. And then, of course, looking at the magnetic anomalies, in fact, luckily we have a pole that reverses, but it leaves positive and negatives and positive anomalies and negative anomalies. And they're not nice, beautiful lines. They're a little bit messy, because as the things erupt, sometimes they're right during the change and stuff like that. So you get kind of ragged edges, but from a distant view, you can see them. And this was, Vic Vacque was my thesis advisor. This was a paper he wrote back in 1961, long before they had these beautiful satellite images where you can see the Mendocino fracture zone, and you can actually see the spreading centers up in here, and then the basin range gravity stuff there in the western United States. And what he had discovered in 1961 was that a lot of geophysics is just pattern recognition. And so he was able to say that this pattern over here had been offset from, it was way over in this area here. And so along the Mendocino fracture zone, you have 1,150 kilometers of offset. And then across the Pioneer, there's another 256 kilometers offset. You can move these back, and you can see here, when you restore this slip, you can very clearly see that those anomalies match up very nicely. And this was all because the Navy was collecting marine magnetics, towing these ships around, and you can see it's kind of boring tracks running east-west for weeks at a time. And as I showed last night, the whole reason, I think, for that was shown in the Hunt for Red October, where they were able to navigate the submarine without pinging by staying right on top of the central anomaly of the Mid-Atlantic Ridge. And they were running down the ridge, and anytime the magnetics started to go off, they made a slight correction. And so I thought that was one of the greatest chapters in marine geophysics I've ever seen. So, and then where you get subduction here, you wind up with active volcanoes, and you can see active volcanoes in here, and then where you're not getting subduction along here, you don't get volcanoes as you go inland into the basin range area. And this is in general, you subduct the oceanic lithosphere underneath the continent, you get down, this is wet, it comes down here, it starts melting here, and you wind up erupting continental volcanic arc. In one case where India is crashing into Eurasia, you actually get the continent going underneath the Eurasian continent. That's why the Tibetan plateau is so high and not lifted. And then one of the things that really helps on plate tectonics is to being able to see the magnetic anomalies, because we can date those based on the reversals and stuff. And this next one will be this area here. And you can see here, there's really nice, well, this is the stuff that's been filtered a bit and a bit dodgy, but anyway, the East Pacific Rise comes down here, the Gulf of California is up in here, and the Galapagos Spreading Center is running east-west here. This is running, this is spreading north-south, this is spreading east-west, and then there was older stuff coming in there. And then this is the area, actually this is Papua New Guinea up here in Australia. You can see south of Australia, there's really nice delineated magnetic anomalies, and those are dated fairly well, so you get a fairly good handle on exactly how fast things were opening. And this is the South Tasman Sea with the abandoned spreading center in it. So the area that I'm going to be talking about now is the Scotia Plate down here between the tip of South America and the tip of the Antarctic Peninsula. And this map, which was produced by NASA, is actually incorrect, because there's no longer an active spreading center running through here. It's a very complicated region, and they can date the magnetic anomalies, but it's clear that it stopped spreading a while back, but there's still some earthquakes, so it's still a zone of weakness. They show it as an act, they show it as just an active spreading center like this stuff here. Okay, this is a map, and this is the Antarctic Circumpolar Current polar front. Main branch of it comes through here. There's the sub-Antarctic front that runs around here and then goes over the Falkland Plateau and winds up in there. And then the southern boundary current runs through there. And what's interesting is this is a wonderful picture taken by NASA Goddard Space Flight Center on the Sea Viewing Wide Field of View sensor, the Seaways. And what you're looking at is shows chlorophyll concentration in shades of blue, lower concentrations to yellow higher. And so this subantarctic front is coming around here. This is Buenos Aires would be up here, Montevideo's up there, and then this is the Argentine Patagonia coming down to here, and you can see where the this subantarctic front curls around here and then comes up here and then spirals, a bunch of gyres coming off of it. And the total transport of the Antarctic Circumpolar Current at Drake Passage is estimated to be around 135 Sverdrups, or 135 times the transport of all the world's rivers combined. There's a relatively small addition of flow in the Indian Ocean with the transport south of Tasmania reaching 147 Sverdrups. And the Mississippi River discharges an annual average rate of between 200 and 7,000 cubic feet per second, which is 7,000 to 20,000 cubic meters, which, when you're talking about one Sverdrup being 1 million cubic meters, the Mississippi River is practically nothing. And the Amazon is like 10 times Mississippi River. But that's why when you combine all the rivers, they don't even quite add up to what this.
Could you go back one?
Sure.
Just real quick. Just a comment. I look at that, and it's amazing the kind of similarity to what you see in the Caribbean. You know, with the two transforms and,
Yeah.
and the front off to the side.
Yeah.
I'd never really thought about it before, but
Well, you're correct, but there's a lot of
No
quite
good-
different stuff
Right.
because here we actually have good magnetic anomalies. We have the abandoned spreading center. We know, when this formed and how it formed. And in the Caribbean, as I showed, it's mostly a large igneous province. There's no way to date the Caribbean Sea the way it is. And so, yeah, superficially, yeah, it looks the same. Okay, now this is some work that Jim Zakos and a bunch of other people did back in 2001. And it's based on diatoms from Southern Ocean cores, and then they have a way of measuring the delta O18. They can tell you what the equivalent of what the bottom water temperature was at times in the past. And so, so this is their temperature equivalent here in degrees centigrade. So starting back in the Paleocene, between the Cretaceous Tertiary boundary, which would be just about here, the bottom water temperature for something like 8 degrees centigrade, they reached a high up here at the early Eocene climactic optimum at about 52 million years ago. But this is what I think is really scary, this late Paleocene thermal maximum. Because as the world's oceans warm up, they wind up melting out the permafrost that's in the continental margins, particularly up in the Arctic, and you get a huge release of methane. And as soon as the North Slope starts thawing, we're going to release a huge amount of methane, and methane is a whole lot worse on global warming than just CO2. So, and I have a hunch that, as we start heating up the ocean, particularly the surface, we're going to see another spike like that. And personally, I don't think we'll survive.
it's not just in the permafrost. There's a good body of evidence that the big Siberian gas fields in Russia, that the actual trap of the gas is the permafrost. So if the permafrost melts there, you not only get the gas out of the permafrost, you may release the gas out of the reservoir.
Yeah. So anyway, have a good day. But this is what stood out like gangbusters, is this just incredible drop in bottom water temperatures in the world's oceans right at the Eocene-Oligocene boundary about 33.5 million years ago. And everybody tried to come up with an explanation for that, and that's when they think that these Antarctic seaways opened south of Australia and between Drake's Passage south of South America. And then what's interesting is the real drop in temperature started here in the mid-Miocene, and then we got really cold down here, and the start of the North American ice sheet was about 3.5 to 4 million years ago. And I think most of those actually had to do with closures of seaways. So one of the things that should be noted on this slide here is this Antarctic Circumpolar Current actually diverts around the South Scotia Island arc here, which has passages between the volcanic islands of 500 meters or so to 700 meters. And so it's the Antarctic Circumpolar Current is actually a surface to bottom current. And so apparently anything that comes within about 500 to 600 meters of the surface is able to deflect the whole thing. This is sort of an idealized version of an island arc. And the other thing that's interesting is the polar front, which is one of the major components of it, actually snakes through essentially the deepest part of this North Scotia ridge. And so having just small variations in the bathymetry can have a huge impact on how big the current is and where it actually goes. This is back to the slide I showed at the very beginning. There's a lot on the geology that says that South Georgia Island was in fact sitting right off of Terra del Fuego in this position here. before it got moved to where it is now. And I don't have a whole problem with it moving. It's just that we can't figure out how it got there. And so this is just some of the geology that defined. One of the things that's interesting about this and about South Georgia is you have all these silicic volcanic rocks, upper Jurassic, and then you have essentially tholeiites, ocean floor basalts that run, well, if you believe ENDL, they run all the way up to Ecuador, but anyway. And so what happened was you had the Fuegan Andes open here, and then they slammed back shut. And so that's why you have all this ocean floor stuff that's now uplifted. And it's the same thing you see in South Georgia. So here's the ophiolites in black, and you can certainly see them all the way up to here, just to the bottom of the Patagonian ice cap, which means they may go further, but we just haven't been able to see them. And the same thing with South Georgia is that they seem to have been two different pieces and then slammed back together. And that's, who knows, maybe that's why they go up to 10,000 feet. This is the beautiful abandoned spreading center in the Western Scotia Sea, offset with a few long transform faults. And then you can see the active spreading center over here in the East Scotia Sea, and this is the South Scotia Island arc. And as I said last night, Sylvia Earle kept referring to it as Google Dirt, and so they finally got around to putting the ocean floor in. You can actually see the spreading centers there very nicely. And they claimed they'd gotten it, they had produced it themselves, and then Dave Sandwell said, how come my initials are in the ocean floor? Because he just embedded his initials at 18 different places to sort of copyright his version. And so that's why Google Earth had to, acknowledge Scripps, SIO, NOAA, US Navy, National Geodetic Agency, and JEPCO. Because
now, on that map, where does that big major current cut through?
Okay, the Antarctic Circumpolar Current actually has 4 different lines on that other thing, but the main one, which is the polar front, sort of comes through here and then comes up right in a very narrow little passage through here, and another branch of it comes up to another fairly narrow passage here, and then swings around this way and then comes back, and then the polar front comes down here, but then detours around South Shetland Island.
And this current is how deep, or is it?
Well, it actually goes from the sea floor to the sea surface. And I hope, well, I'll show you some really neat images of it shortly. But anyway, these are the magnetic anomalies that have been identified in the Scotia Sea. Anomaly 8 is about, anomaly 6 is about 20 million years ago, 5 is about 10 million years ago, 8 would be 28 million years ago. So we know that this part of the Scotia Sea opened in this way. And at one point, ENDL and I wrote a short paper about how South Georgia got to where it is. South Georgia would be way over here. We referred to it as the bank billiard shot because we thought, well, maybe somehow it opened this way and then hit and went up that way, but the jury is still very much out on it. These are magnetic anomalies, so you can see some of the reasonable delineation. I mean, it may take some imagination on a lot of people's part, but so we think this opened, the West Scotia Sea opened from about 28 million years ago to about 6 million years ago, and Peter Barker originally thought that then this opened here from 21 to 7. We've got some dredges now from the couple of cruises we went on, and this is much older than that. And then the East Scotia Sea is not as old as 15, and it's only about 10 million years. Luckily, there's still a lot of interesting things we really don't know the answers to. This was the map again. This is, Dave Sandwell did the satellites measure the distance between the satellite and the sea surface, and it's called satellite altimetry. And the thing that I like is if you're in a ship leaving Tokyo and you sail east across the Japan Trench, you actually go down 75 meters and then back up, because gravity attracts things. So seamounts would be a positive thing, and trenches would be a negative thing because the water flows away instead of towards it. And so here you can see beautifully the Antarctic Circumpolar Current coming down here around Campbell Plateau off New Zealand here, and then it goes through some of the deepest parts in the South Pacific Rise, Antarctic Pacific Rise here. And this is where it is going through Drake's Passage and then curling up here, and that was the chlorophyll shot that I showed earlier.
But back between Africa and Australia, what causes that big notch? You see where it's kind of headed south, and well, in fact, here you got the little yellow things.
Yeah, that's why I put the yellow things
good.
up. The yellow things are large igneous provinces, and so they're sort of submarine plateaus that come fairly shallow. And so you can see here, Kerguelen Plateau and Heard Island and Kerguelen Island are a couple of things here. And so it comes down here, and it hits this, and it can't get around it, so it goes back to the north, which it doesn't really want to do. But anyway, then it gets down here, it goes through the deepest parts of the ridge here, and then runs into Campbell Plateau, gets diverted around it, and then heads back north, and then tries to get through the Pacific Antarctic Ridge along some of the, appears to be along some of the major offset transform faults, which seem to be some of the deeper features. Okay, this is what the world looked like at about 180 million years ago, according to our model. This is getting to be a little old, but we haven't changed this a whole lot. This is the mantle plume that came up under Africa that split the continents apart. So, too bad Julian's not here. And this is compared
You're being recorded, don't worry about it.
All right. And Ron Blakey, who does these absolutely gorgeous artistic renditions, where he does paleogeographic, so he says there's deserts here and stuff like that. This is his 200 million year reconstruction, and I would say in general it actually looks very similar to ours, except I would object to having the Central Atlantic opening by 200 million years, because that's the time where the Central Atlantic magmatic province came up and started splitting the ocean apart. So I think he's a little bit premature on this. And then there's this professor, Scripps, Jerry Winter, who just passed away recently, but he said, I'm tired of always seeing a Eurocentric view. I want to see a Pacific-centered view. And it actually was kind of eye-opening, because it means that back in the middle Jurassic, there was just one ocean. And when you start looking at ocean circulation, of course, as the Earth rotates, the water is going to travel this way. And
is that Australia and New Zealand upside down there?
This is Australia, New Zealand's in pieces down here. This is India before it's breaking away, Madagascar, pieces of Africa, South America, and stuff like that. So it could either hit there and sort of then get gone up to the north, but the other thing is you wind up getting what's called halothermal circulation, which means that the water starts evaporating. Of course, it concentrates the salinity, and it gets denser, and so it just drops down. And so you have this warm bathtub here that's essentially hot all the way from the surface nearly down to the bottom.
You can see it on this. If you look over there, North America is in yellow.
Yeah.
And the Gulf of Mexico,
It's not open.
It's not open, and when it started to open, as near as we can tell, it actually opened from the Pacific side.
Yeah, I agree totally with you, and I'd love to talk about this with you, but that's another talk.
Well, and just very briefly, it opened very episodically. It opened a little bit, let in some water.
We need to argue about that.
And then, well, this is how do you explain all the low end salt?
There's people now that explain it being deposited in 25,000 years.
Whoa.
So that's why we need to discuss it.
Okay.
Let's go get a
I
beer.
don't believe that either, but,
Yeah.
but anyway. So by 120 million years ago, the central Atlantic is starting to open over here, and you have what's called the Tethyan Seaway over here between Africa and Europe. And so you wind up getting what I call a circumequatorial current. And so this thing just keeps whipping around the world, and it actually starts getting the Pacific even warmer than it was in the Jurassic. So if you look at long-term deep sea temperatures, it actually starts getting really hot during the Cretaceous.
What's the black smudge?
The black smudge. Oh, these are the identified magnetic anomalies.
Oh, okay.
And so this part of the Pacific Ocean is still here. And I think this is the Anton Java Plateau. And so these are some very old marine magnetic anomalies that date back to Jurassic, early Jurassic time.
So is another way to think about that, everything that's white in
Has
the
been
Pacific
subducted.
has been gone.
It's gone.
Yeah, that is a very interesting view.
So, whoops. Yeah, and so then, because here now we get more anomalies that are still in existence, and we can see the anomalies being formed in the Central Atlantic and the South Atlantic. And by 60 million years ago, at the late Paleocene, you still have the circumequatorial current, but it's being pushed north as Africa goes north, and by this time, it's almost up to 30 degrees north. And so, and that's just before when India essentially starts colliding with Tibet, is right in this time. And when it starts colliding, then it finally shuts off that seaway. And what happens is, and then this is another way of looking at the same thing, showing the Antarctic Ice Sheet. This is a more recent one than the previous thing. And so you can see that Jim's smoothed out this drop and flap area, then things there. They think that was originally some trying to stitch together two different data sets, and they weren't doing it quite right. So here you can still see a significant drop at the Eocene-Oligocene boundary, but then it's kind of jumpy here and actually getting a little bit warmer until the middle Miocene, and then it starts getting a lot colder. And so at 60 million years ago, it's going north of Africa, and at 50 million years ago, this is shut off, and it's now going south of Africa. So you're going out of the temperate, or out of the tropical region into the temperate. And so it actually has to get down to 45 degrees south, and that's why it starts cooling the whole oceans. And so that keeps going. 40 million years ago, 30. As you can see, the black smudges are getting more common. 20 million years ago, it's getting a little bit tortuous. It's coming between New Guinea, Papua New Guinea, and Southeast Asia, Indonesia, around the southern margin of Africa, up here through the Panama Canal region, and you're actually getting development of a Antarctic Circumpolar Current because this seaway is clearly open, and that's open as well there. And as you can see, and so by this time, this is at 20 million years ago, and then it starts getting a lot colder at that point. By 15 million years ago, we think this has been pretty much shut off, and there is a current that goes through the Lompoc Straits, which only is like 700 meters deep, and it's a very strong current, which sort of snakes through this area presently, but you can see that as you close everything off, it causes all sorts of other problems. And then the major factor that I think happened was about 5 million years ago, you close up the Isthmus of Panama, and so you essentially stop having any pretense of a circumequatorial current, and you wind up going into all these cyclonic gyres, and so you then have the Gulf Stream coming up. This current, can't go through here anymore, so it comes up here as it evaporates and gets heavy, dense, warm seawater gets up in here. Norwegian Greenland Sea sinks like a rock, gets cold, comes back down, and this is Arnold is conveyor belt and comes down here and then starts really ramping up the Antarctic Circumpolar Current.
That really gives you a good reason for the Arctic forming.
Yeah,
At 3 million.
yeah. Because once you closed up that seaway,
It ain't warm anymore.
it's not, yeah. And then you start, and so you still see, the equatorial surface current in the Pacific, and then it comes up back to like Kuroshio current here. Of course, the Gulf Stream shows up like gangbusters in this area here. It's amazing what satellite images can do for you.
You said that's on fluoride or
Right.
fluoride? What's the lighter color there? It's
Oh no, this is totally different thing.
okay.
Yeah, this is simply satellite altimetry.
Okay.
It's the median along track slope difference in microradians in milligauss.
Sure. Thank you.
And if you want to, I can get you in touch with Dave Sanders.
No,
He can
thanks.
explain it.
Chlorophylls, which
Yeah.
So anyway,
plankton.
this is back to the Antarctic Circumpolar Current going through Drake's Passage, and again you can see, the South Shetland Island arc here is a real barrier, and the stuff gets wrapped around it. And I'm going to run out of time on this. Okay, one of the things we looked at on the 2008 cruise is this object there, which we wound up calling the Starfish, which was supposedly no more than 21 million years old. And we got some beautiful C-beam bathymetry data, and that stuff is just gorgeous because we found this really nice cliff. We were able to get some really nice dredges there. We were able to dredge this. We tried dredging this stuff up here, and we couldn't get a steep enough slope, and it was all covered with mud, so we failed to get very good dredge results from that. But we did get, this is what we call the Starfish that I showed in the other image. We got really good results from dredge 3 and 2 and 6. I don't think we got much, and then 7 and 8 and 9 and 5. And also there's some clearly lineated magnetic anomalies there, and I've tried forever to figure out how to correlate them with some time scale, and it just doesn't work. What we did find was that a lot of these rocks do look like very nice island arc. These are the yellow are the South Shetland Island arc. Blue are the western Central Scotia Sea, and the northeastern Central Scotia Sea or oceanic basin type stuff. And this is just a comparison in visible size. This is the starfish that we looked at. And the starfish is now sitting at about 1,000 meters or so, maybe a little deeper. And then the present South Scotia arc has the islands here, and these are exactly the same size-wise, so you can see that this actually looks, could be very similar to something like the island platform that those volcanoes are on. And so Peter Barker dredged a couple of dredges out here on the South Sandwich 4 arc, and he had dated those at 28.8 million years and 32.1 million years. And then on our dredge here on the southern margin of the Starfish, we got 28.6. And so the presumption is that if you closed up the East Scotia Sea, that part of the arc would be over here. This would be also part of the arc. But then you get down to dredges 34, 32, and D2, 34, 32, and D2, and they're about 11.5 to 16 million years. So the arc, we think, in this position was certainly active between 32 million years and 11 million years, which would cause a lot of damming up of a Antarctic Circumpolar Current, because it would come through here, but you still have the Falkland Plateau and other things, and it may not have a very easy way of getting through there. And so Oh, all right. That sort of ends part of that. We still have some time, right? Okay. This is now showing what we did on the last cruise.
We'll try more constrained, but you had to get that over.
This is E and DL. I don't know who that guy is. And then a bunch of students and stuff like that. And what was absolutely astonishing was the South Georgia Island representative, who was this guy here. He comes on board, and the person that's not shown here is one of our techs. And it turns out these two guys had been on the same fishing boat in Alaska as 4-member crew about 12 years before, which I think also helped our relationships with the South Georgia government. And then we had a couple of people that were our whale watchers. One was back here, one was here. And now, if you want to do any seismic work at sea, you have to have marine mammal observers on board, and they will tell you to shut down if a whale or something gets anywhere close to the ship.
Did you have to shut down, Trevor?
A couple of times, yes. But luckily, they were relatively kind to us, and they had to be, there's all sorts of distances. We were actually just using tiny little air guns. I mean, we weren't using these huge things that the oil industry tows around. So, and then this is Jillian, who was our junior high teacher from Flagstaff, Arizona. And this was our ship track. And we had this wonderful passage out here, and we got to Bird Island, where we wanted to put in the first GPS station. And we came to a dead halt, and the waves were 30 feet, and we couldn't get the Zodiac ashore. And everybody was terribly disappointed, particularly the people on Bird Island, because they wanted some fresher food. And so then we headed off from there, and we really wound up, and then we did a couple of seismic lines out here. And then here, we were just wasting our time because the seas were so rough and the things were so bad, and we couldn't really do much of anything. And we were getting really disappointed, and then finally we got some break in the weather. We were able to get to a GPS station here, and then went out and did a bunch of work down here, and then finally we were able to get that station in there, which is the one I showed you with that magnificent picture. This was Bird Island, where we put in one of the seismic stations at the very tip of South Georgia. And this is just general things that you see at sea down there. And then this is some of our multi-beam data as we went out there. We got some really nice data. We wanted to run out here to the Northeast Georgia Rise because one of our tectonic theories is that South Georgia, as it was moving away from South America, it ran into Northeast Georgia Rise, and it just stopped dead because it's a large igneous province and it couldn't get past it, and couldn't subduct it and stuff like that. And so it kind of stopped there, and then Ian Dale hates my image on this, but East Scotia Sea pops out like a hernia, and because it wanted to keep going. This was the streamer that we were using. Wasn't very long, just a few hundred meters, and then relatively close spacing on the sites. But we did get some really nice seismic results. Most of these are chondrite deposits, for people who know what chondrite deposits are, and it's just a mess. But they're beautiful images.
I can't read the scale on that. What, you're getting down about 5 seconds?
This one is 4.1 seconds.
Okay, 4 seconds.
And I think at most we saw maybe a second or second and a half at the very most of penetration on this, which is equivalent to about a kilometer, a little bit more. But we did see some absolutely stunning images on it. And this is South Georgia. This would be the stuff coming into it. You can't see this too well, but one of the things that we did see was that, as we thought, or as I hoped, is that the eastern line, where they hadn't quite collided, the stuff would be relatively unperturbed. Which you can see, this is relatively flat line here. And then the more western line, where they had really collided, you just couldn't see anything because they were totally collided. Okay, this is King Edward Point, which was a major whaling station. It's where the British Antarctic Survey actually has a base there. And professor from the University of Luxembourg had actually installed a GPS station here. So then we finally started cooperating because, you know, if you have one GPS station on a table like this, the table can be tilting and rotating and stuff, and if your point happens to be right at the pivot point, you're not going to see anything. But by putting one at that end of the table, this end of the table, and that side of the table, you get a really good handle on how the whole thing is rotating and moving and changing. And so this was the one that had been installed, and then we installed these 3. And these are some, the interesting thing is, one really, you know, talking about plate tectonics, we don't know whether the boundaries on this side of the whole thing are on the other side. And there's some earthquakes down in here suggesting some sort of subduction and stuff. And so there's a lot that we still have to learn. There we are, that's the Palmer, and there they are headed out to look for GPS sites. This is Schmoon Cove, which is on the eastern end of South Georgia. Absolutely stunning setting. Unfortunately, because of all the protections in South Georgia, the only people that were able to go ashore were the ones that were actually installing the station. So the rest of us had to sit there on the ship and look at it through binoculars. But you can see these are where the truck batteries go. They have anemometers or wind things. This is to transmit the data up to a satellite. And then the solar panels are down on this side. I think this is, no, which, anyway. So they're pretty big installations. And you can see sometimes the weather was pretty awful. A lot of times the weather was pretty awful. And luckily, you know, undergraduates are much better at this than I am. 70-pound packs, lugging things up a long ways. And then trying to connect everything into their hands to get cold. Oh, and then one of the things we did, these were a couple of seamounts that were sitting off, they're just off here off South Georgia. And by filling in the multi-beam data, this was data that we collected in, I think earlier, and we were able to dredge some rocks, and we were actually able to get things which I think were volcanic, and we're just now possibly getting some dates on them. But I think these images are absolutely stunning, where you can see these 2 seamounts, and they look very different, but this is obviously, I think it's been close to sea level and had the whole top flattened off on it. And the other one, kind of maybe just that part got up to sea level. We had one dredge from the previous cruise in 2008, which gave a date of like 81 million years ago. And that's why we really wanted to get a handle on that, because that would really blow apart a lot of the thinking on these things. And we think one of the things that may be happening is that this thing somehow collided with it and formed this ridge here, and the whole thing is bent up. And I think I have, and this is what it looks like on the seismic data, and so we still have to figure that one out. And then, oh, and Jillian would, she had a couple of satellite communications with her class and stuff like that while she rode the ship, got all the students excited. And you do see a lot of penguins, and this was the one on Anakov Island, which was the special protected area. I think because Jillian, you know, had her eyelashes, the guy from South Georgia, she was allowed to go ashore. The rest of us weren't. But the rest of us were able to go on, I mean, we could get on the Zodiac and go that close to the shore. So we were able to get some really good photographs. And of course, there's lots of elephant seals. And those are the solar panels in full view there. So that's how they run the whole thing. And, that's the, I think, Bird Island. That's Anakov Island. And the scenery is stunning. If you ever have any desire to go on an Antarctic cruise, I strongly urge you to try to go to South Georgia as well, because it's just one of the most amazing places. And when we were able, at Bird Island, because it's a station, we were actually able to go ashore and actually, quote, help set things up. And you'd be hiking up this very steep thing, and all of a sudden we're almost nose to nose with an albatross. And of course, you weren't supposed to come anywhere near them, but if you couldn't see them in the fog, it's not really your fault. And
You said the elevation is 10,000?
yeah, the very top of South Georgia, we never went above a few hundred meters. But, and then I show you this because this is hot off the press. This is the data that we just got about a week ago, based on about, would be almost 4 years now of 3 years of the GPS data. And South Georgia is down here, and you can see the 4 stations in here. These are relative to South American, and you can see the South American things are in all different directions. And so essentially South America is, quote, somewhat stable, and there's a couple of stations that's Falkland Islands, and you see very small northward motions with respect to South America. And what's really interesting, and unfortunately it doesn't show too well on this slide, but hopefully this next one will show it a little bit better. This point here, which is on the southern, this is Ushuaia on the southern tip of Terra del Fuego, and there's a major plate boundary that goes between this station and this station, although I think it may be questionable whether that boundary is directly there, or maybe closer to that one. And you can see that relative to South America, this bit of Terra del Fuego is actually moving eastward that far. And what we found with the stations that the ones that we installed, as opposed to the one, the King Edward Point one, we see movement like that. And somewhere there's a scale. I mean, this is not huge amounts of movement. I mean, we're talking about millimeters per year. But it appears that South Georgia may in fact be moving with part of the Scotia Plate, rather than, as we thought, had collided with northeast Georgia Rise, and then was now moving as part of South America. So we still need probably a few more years and some more data collected. But
And those stations will be there how long?
well, supposedly the grant is expiring, I think, a year from now, because you always get one extra year. And we hope to give them to either the South Georgia government or the British Antarctic Survey, because you really need like 20 years worth of data, and it would be absolutely absurd. And plus, we put them in places that you really can't get them out. So,
As you know, looking at your solar panels
yeah.
and those sea lions, you just
Oh, yeah.
you kind of go, when's this? How do they react to the seal rubbing their backs on and stuff?
Well, we were wondering how they were going to react to the seals trying to mate with the solar panels. So.
Yeah.
No, we really were very concerned about that, and that was about the only place that they could find, because you need a solid piece of genuine rock to install this, or else, you know, in the early days they installed them on buildings and stuff like that, and you think, you know, huh? The wind blows and the thing moves around.
Right.
So, anyway, all right, only 3 minutes late. So,
Not bad.
yes.
You know, on those seismic slides that you showed,
Yeah.
they look really clean compared to things I see on the internet. Is that because of advancements in the technology, or what's going on there?
Well, I think it really depends upon what you're looking at, and some things come out looking pretty good. Other things, you know, are a mess. And the oil companies have multi-million-dollar, billion-dollar labs that sit there and process this stuff. And as I said the other day, you know, that finally the technician gets annoyed and says, well, what do you want it to look like? So they process it so that they bring out whatever the boss wants. Unfortunately, we deal with graduate students, and so we have to train them, and sometimes it doesn't work. So,
You said those are about a kilometer depth?
yeah,
Looking
there's no more than a kilometer.
a year. It's a high resolution survey
Yeah.
as opposed to petroleum companies are looking kilometers.
Oh, yeah, no, and they usually have,
Yeah.
you
You
know,
know,
huge arrays and.
Typical streamers.
Not
Yeah.
as high frequency.
He had a single line behind the boat, and it
Yeah.
was fairly short.
Yeah,
A typical full-on seismic for oil industry, they'll have like 7 to 10 streamers
Yeah.
behind a boat that they're pulling simultaneously, and they will be 4 or 5 miles long each.
yeah,
Right.
yeah, and you worry about fishing boats going
Well,
across them.
and turning that, just think of all that wire out behind you and trying to turn it.
Yeah.
But, and then once you get the data, you got trillions and trillions of digits, but then think of it like what you can do on your pictures when you get them on the computer and you can focus things and change all the, well, you're basically doing that to these images where you literally are putting things back where they really belong, and you are tightening up the resolution.
Hey. Yeah,
Is there any type of shipping that is passing through there on a regular basis?
tourists.
Just tourists?
Yeah.
Nothing else?
Seasick tourists.
Well, yeah, it all depends. I mean, sometimes you're lucky and it's not bad, and other times it's bad.
Twice a year?
Well, and then they do have a couple of supply ships that go to South Georgia. I mean, there's not more than, I think, maybe 20 people that overwinter on South Georgia. Well, maybe 30. There were 4 at Bird.
And that's actually a country and that's their capital?
Well, I mean, I wouldn't call it a country. I mean, it used to be a protectorate of the UK.
Yeah.
And then with all the conflict with respect to the Falkland Islands and Malvinas, they, sort of separated out, because they used to be, strictly under the Falkland Island dependency. And now they're a different branch, and I mean, their whole economy comes out of the UK government. But, and it's almost exclusively scientists that are there. Although I do think apparently there's a couple that run a sort of museum at King Edward Point, which is one of the old whaling stations. So,
Who goes to the museum?
tourists?
Or the tourist ships?
When the
Yeah.
ships, when the
Oh,
ships
yeah.
stop.
Tourist ship. And Peter Barker he was out on the cruise in 2008, and then he passed away, and he had done an awful lot of work on the Scotia Sea, and his wife actually got permission to scatter his ashes in the graveyard where Shackleton's buried there. That was, I thought, very nice. So she went down on a tour ship and was able to scatter the ashes. So.
The dredge samples are pretty much all the salts, what kind of remember?
No, the dredge samples are almost all glacial erratics. And so you have to sort through all this crap to find a few little rocks that might be volcanic. So, it's,
No coring down there?
yeah, there's coal. And,
Offshore.
yeah, yeah. And in fact, we did, actually there's some heat flow that we did. And actually we loaned our heat flow gear to Peter Barker, and he went down and he said, well, wasn't working on a couple of stations. And I said, well, did you get full penetration? Yeah. And was there, was the thermal gradient 0? And he said, yeah. I said, well, it was working because back in the late 70s or something, they had had some other heat flow and they'd gotten exactly the same results on 2 other stations. And my supposition is that somehow some of the Antarctic bottom water got sloshed into the Scotia Sea, cooled the whole thing off, and then, screwed up the thermal gradient. So, anyway, yeah. So there are cores. I don't know that deep sea drilling's ever drilled anything in the Scotia Sea.
It'd be tricky to, in those kind of currents, that would be tricky to stay on station.
Well, I was on, the only time I've ever done any ODP or deep sea drilling work was in the Woodell Sea.
Okay.
And I was actually on the Danish support vessel, and we were supposed to be able to tow icebergs.
Right.
Bloody chance of that. But we had much better food than they did on the drill ship. So, but that,
So those rock samples, they were pretty much all erratics.
yeah,
The
yeah,
trade-
all of those are, virtually all of those are erratics. And, you know, who knows where they're from. One of the first times I was there was with Peter Barker, I think it was back in 82 or 83. And we were going across the Scotia Sea, and we had to detour around this iceberg that was like 120 kilometers long. It took us 6 hours to get past it. And, you know, had a beautiful run. You know, it was flat, calm, it was actually gorgeous. And then we got up between the Falkland Islands and Argentina, and we were down to 2 knots trying to steer into the wind, and the ship was crashing up and down. And we got to Montevideo, tied up to the dock, and the bilge alarms kept going off. That's because they had split a seam and the ship was actually sinking in the dock. Luckily, I was getting off there. But the poor people who were headed back to England, they did a damage assessment, and they finally decided that, you know, as long as they were underway, it wasn't going to sink. I'm glad I was getting off there.
Who wants to volunteer to go for the ride? It must be some pretty nasty sailing down there.
Well, it's interesting, and I've been, you know, times I've crossed the Drake Passage, and it's nice, flat, sort of rollers, and, you know, you can be out there in sandals, well, you can't wear sandals, out on the deck, and it's just gorgeous. And then other times you can't even stay in your bunk. One time we got into Ushuaia, this was on an Italian research ship, and a bunch of the tour ships had just docked as well, and on one of them, somebody had gotten up in the middle of the night to use the head and got slammed into the door jam and got killed. So,
Yeah. Yeah.
But it's beautiful out there. So, anyway, thanks for
Thank you, Larry.